Hello everyone, I'm Josh and welcome back to my tutorial on how to solve scattering problems using Lumerical's FDTD software. So in the last video I kind of ended on how to add frequency domain plane monitors into our FDTD simulation. Alright, and here's kind of where we left off. So just to review quickly, we set up the simulation domain where we put PMLs as the boundary conditions. We added a total field scatter field source that injects a plane wave in the x direction, polarized in the y direction, and only the plane wave will only enter the region that is in this white box, which in this region we also included a sphere, which which is a silver sphere. We added a video monitor, a movie monitor, so we can watch movies of what actually happens during the time domain simulation, and we added a simple frequency domain monitor on the outside here. Now, we never actually got to talking about how to calculate a scattering spectrum using Lumerical's FDTD. I did hint about how we could do it at the end of the video, but now I'm going to go into the actual details of all this. Alright, so again, this is the scattering problem. We have a plane wave coming in. It hits some sort of nanoparticle, so I kind of showed this weird shaped silver nanoparticle, and the waves scatter off of it in all these different directions. Okay, so now I'm going to go through the theory of how to deal with these sorts of scattering problems. So the first thing that you would do theoretically is you would draw a sphere around the particle, preferably pretty far out. And I'm saying that the sphere has a radius of a. And over this sphere, you want to know the electric field, the theta and phi components of the electric field, and the theta and phi components of the magnetic field in the frequency domain. So if you're doing this calculation in the time domain, then you would need to take the electric and magnetic fields over the sphere and then Fourier transform them to the frequency domain, which we know we can do already in FDTD. Okay, next we would then calculate the Poynting vector over the sphere, the radial component of the Poynting vector over the sphere, because again the Poynting vector is a vector, so it will have a theta and phi component as well. But if we want to know the scattered power, we only want to know the power that's leaving the sphere in the radial direction. And we can get that by just using this formula here, where H star is just the complex conjugate of the magnetic field, and Re means that this is the real component, because these values are actually going to be complex in general, and they depend on frequency. So once we know the Poynting vector over the entire sphere, we now can calculate the scattered power. And to do that, we just integrate the Poynting vector over the entire sphere. So what we're going to be left with is just a value so the power is just going to be a number that depends on the frequency that we are interested, or the frequencies that we are interested in. Okay, now if we divided this, okay, actually I should just pause here for a second. The scattered power is enough to have a spectrum. All right, so if you plot power as a function of frequency, you will have a spectrum, but it doesn't really tell you all that much, especially in a FDTD simulation where the pulse is just like an arbitrary waveform that has all the frequency components you're interested in. So to get any sort of useful information, we typically want to divide by the intensity of the incident pulse. And because we have a power, which has the units of watts, and we have an intensity, which has the units of watts per meter squared, the power divided by the incident intensity was going to have the units of meters squared. So this is why we call this the scattering cross-section, or the scattering cross-sectional area. This is kind of the effective area of the scatterer. So this is what's neat in scattering problems, is that though your particle has this, let's say this area here, right? This is the real area of your particle. The amount of the electromagnetic field that it scatters away is actually going to correspond to an area that could be bigger than the particle or smaller than the particle. Okay, and finally, so if we take this scattering cross-section and we divide it by the actual area of the particle, we get the scattering efficiency. I didn't actually label that here. Oops, sorry, this is all a mistake, so I'm just going to get rid of this here. This is the scattering efficiency. So if this is equal to 1, it means that at that frequency, this particle scatters as much wave as you would expect it to based on its actual area. However, if it is greater than 1, then it's considered to be a good scatterer because it's scattering more than you would expect from its area. And if it's less than 1, then it's a bad scatterer. Okay, so this is how you would do it theoretically. Just a quick review. Calculate your electromagnetic fields along a sphere. Calculate the radial component of your pointing vector. Integrate the pointing vector to get the power. Divide the power by the incident intensity to get the cross-sectional, cross-section spectrum. And we can get the scattering, efficiency. Sorry, I'm just going to correct this here. Efficiency by dividing the cross-section by the actual area of the particle. And I should mention that this is not always done because sometimes it's hard to find the areas. If I told you to find the area of this, it would be difficult. You could do it numerically, but yeah, that's up to you to do. So now we want to do this in FDTD. So in FDTD, it's a bit difficult to draw a sphere around our particle and do what I did above there because everything's done here in rectangular coordinates. So we need to deal with this in rectangular coordinates. So in my last video, I showed you that in these sorts of scattering problems, we have a total field and a scatter field region. Right, the total field region is where we inject the plane wave, and the scatter field region is the electric field that gets scattered. And we have a PML. From after this slide, we're just kind of going to ignore the PML, but just know that it's there. And I'm going to use this diagram continuously. So just know that in this direction is the X direction, and going up is the Y direction. And I'm assuming that there's going to be a Z direction out of the screen, but obviously I'm not going to draw a 3D diagram here. All right, so to calculate the scattering spectrum, we need to set up 6 plane monitors in the scattered field, one for each side of the simulation domain. Again, because we only have a 2D cross-section here, I'm only showing 4, but there will be one out of the screen and into the screen as well. So those will be 5 and 6. Okay, so plane wave monitor, plane wave monitor, plane wave monitor, plane wave monitor. Plane frequency domain monitor. You understand what I'm trying to say. I'm not editing any of this, so you guys can enjoy my mess ups. Next, we want to, kind of like what we did before where we had the radial component of the pointing vector, we now want to get the normal component of the pointing vector for each of these planes. So here, because the normal points in the negative x direction, we want the negative x component of the pointing vector over this entire plane. So as a function of y and z and frequency, omega. Up here, we're going to want the pointing vector in the positive y direction as a function of x and z and frequency. Over here, we want the pointing vector in the positive x direction as a function of y and z and frequency. And finally, down here, we want the pointing vector in the negative y direction as a function of x and z and the frequency. And of course, out of page, we're going to want the pointing vector of positive z, and into the page, we want the pointing vector of negative z. Next, we integrate each of these pointing vectors along their respective planes. So for example, P1, we're going to integrate the s of negative x over all y and z on this plane monitor, and that's going to give us P1, the power leading in this direction. Similarly with P2, we're integrating the pointing vector over the plane monitor 2, and that's going to tell us the power going in this direction. Similarly, P3 will tell us the power leaving in this direction. P4 will tell us the power leaving in this direction. P5 will tell us the power coming towards us out of the screen. And P6 is the power going away from us into the screen. And once we have these powers, we can simply calculate the scattering power by adding those up. P1 plus P2 plus P3 plus P4 plus P5 plus P6. And again, these are all functions of frequency. And once you have the scattered power, you have your spectrum. You can divide that by the incident intensity to get your cross section, and you can divide that by the area of the particle to get your scattering efficiency. But that's all stuff that you can do on your own and simple arithmetic. So now we're going to hop into Lumerical, and I'll show you how to do this, but in the simple way. So I mentioned this at the end of the last video. Lumerical actually they have this cross-section measurement already set up for you. So first you go to Analysis, you click the downward arrow, you go to More Choices. Okay, I'm just gonna make that bigger. We now go into Optical Power, click on that arrow, and click on Cross-Section. There's actually a lot of different things you can do here. You can even get the absorbed power. I don't know how they do it with this specific monitor, but I will show you another way to do it using the same cross-section monitor. But let's double click on this. And we get the cross-section monitor. If you don't see it, just zoom out and you'll see that they put it in this big ass box here. Again, we don't want it to be that big because we want that cross-section monitor to be in our scatter field region. So we just right click and we edit object. Actually, before we do that, let me just show you what this actually is. So Lumerical, it's nice of them to give us these monitors, but all they are is just the ordinary frequency domain monitors, but they put that in their own little sub folder and they set it all up for you. So that's very handy. So you can see here there are 6 plain monitors. There's one in the negative x direction, one in the positive x direction, one in the negative y, one in the positive y, one in the negative z, and one in the positive z, just as I showed you here in the PowerPoint. Okay, let's go back and let's right click and edit the object. So the way that Lumerical does this, they actually have a built-in scripting language, and they actually have a script that sets up these monitors all for you. All you have to go and do is go into variables, and you need to tell it, well, where is this centered? Well, we want it centered at 0, 0, 0, as always. And then what's the size of the scattering box monitor, as I'm going to call it. And we want it to be, again, we want it between, we want it in the scattered field region, so we need it to be between 160 and 200, so I'm going to say 180 nanometers by 180 nanometers by 180 nanometers. Okay. And now you can see, so I'm just going to click the magnifying glass again, and here you can see we have our cross-sectional monitor inside the scatter field region. Now, just for practicality, click on the Yi cells, the Yi cell option here. Kind of zoom in, if you can. And you're going to want to have a few cells between the total field scatter field and the scatter field box monitor. All right, so here we have about 4 cells, so that's pretty good. Typically in my own simulations with my own code, I like to put around maybe 5 to 10 cells in between, and same between the monitor and the PML. You also want about 5 to 10 cells. Again, with Lumerical, you're restricted in memory, so just make sure that there's a couple cells in between everything. Okay, so now let's open this up and let's kind of go into, let's see what it's actually going to do for us. So we click on Analysis, we go into Script, And here is actually the script that it uses to analyze all of this data. All right, so what's it doing? Well, here we can see that it's going to say at monitor 2, get the transmission data, and it's going to call that px2. So what that is, px2 is just going to be this integral here. So it does that integral in the background, and you can call the value, the result of that integral, by just using this transmission function. All right, px1 is just the negative transmission of px1. So instead of doing the pointing vector in the negative x direction, they just take the pointing vector and make it negative, which is also something you can do. Similarly for py, they just call the transmission function for the y monitor, and py1. And essentially once they get all of that, they calculate their scatter field by just adding up, as I showed you, px1 plus px2 plus py1 plus py2 plus pz1 plus pz2. Here they multiply by the source power, and then they divide by the source intensity. Yeah, again, this is all just how they do things in the background. But cross section, what you're going to get out for cross section is just the power divided by the incident intensity. All right, so that's kind of just showing you what they are doing in the background. This is kind of the script that they wrote themselves, so it's kind of guaranteed to work. But I don't want to go too deep into their scripting language because I'm not quite an expert on that. I prefer to set it up by hand, or I prefer to use their Python interface. Okay, let's okay this. And let's just run this. Before I do that, actually, what I want to do, sorry guys, what I want to do is I want to go into monitor 1, and I'm going to click on set global monitor settings. Remember last time I gave us 21 frequency points? I want a few more here, and you'll see why in a bit. So 51, apply, okay, run. So I don't know how long this is going to take. Hopefully it doesn't take too long. Okay, here we go. We're making some progress here. So you can see that it takes a bit longer if you're doing more calculations, right? You add in some more frequency points. We now have 6 new frequency domain monitors, so it takes kind of a bit more time to get things going. But now I want to kind of show you something here. So if we were to right click on this and visualize, all right, cool. So if we visualize T here on X1, so what is T? So on all of these power monitors, even on this one that we set up in the last video, I showed you that T was just, it just gave you a number as a function of the wavelength, right? And so T is just, oops, where is it? T is just this. It is just the integral of the pointing vector over the power monitor. That's all T is, right? So all they're doing when they do this cross section is they're adding up those T values from each of these 6 monitors. Hopefully you understand what I'm trying to say there, but yeah. So now we can visualize, so just right click on cross section, visualize sigma. So sigma is just the cross section of the scattering cross sectional area, I believe in the units of meters squared, of our nanosphere. And here's what we get. So this is the scattering spectrum. So the reason why I picked more frequency points is so that the spectrum kind of looks smoother, because if you only had 21, it would look like, you know, a bunch of just like straight lines connected to each other. But as you can see here, our scattering is maximized at around, what, 410 nanometers? So if you sent in just like a laser at 410 nanometers at the sphere, you'd get the maximum scattering that you can possibly get out of the sphere. And we can actually test the validity of this by comparing to an analytic formula. So there is something called Mie theory, and the Mie theory is the analytic solution to electromagnetic scattering from spheres, and it was solved by Gustav Mie back in the early 1900s. I believe it was 1910. Let me see, Mie theory, Mie scattering. Let's see, is it, they probably cite his paper. Oh God, how is it not the first thing cited? Let's see, here we go, 1908. Crazy, that long ago. And it's one of the most complicated solutions to Maxwell's equations. But you can write your own, once you find the details of the mathematics, you can write your own code, which I did. But just for fun, what I'm going to see is if there's a Mie theory calculator online, and I think I found one here. Okay, so this here, you need a refractive index. I want a Mie theory calculator that has the materials built into it. Here we go. All right, so we're gonna go with silver, core diameter, 50 nanometer core, no, 100 nanometer core diameter. We want 0, so we don't really need a shell. And we want to go from 200 to 700 nanometers, and the medium refractive index is going to be 1.0. So I'm just kind of redoing what our simulation did, but using the analytical calculation. So we create plot. Let's see what we get here. Okay, I can't shut off the other things. So let's compare. So here they show the scattering as the red line. So as you can see, we have the red line, it goes down. It has a dip at around 320 nanometers. Here our dip is around 300 nanometers, so okay, it's a bit off there. Let's go up and we get a peak at around 410 nanometers. So yeah, that makes sense. 410 nanometers, and then we go back down again. And so as you can see, our results actually agree quite nicely. And this is, I believe it's 40,000 nanometers squared. I'm sure if we did the math, this would be around 30 nanometers squared. So the results agree quite nicely, but it's still going to be a bit off because we're using a really coarse grid. To get high accuracy plasmonic simulations, you want a step size of about a nanometer or 2 nanometers. And we are using, I forget. Yeah, we're using 2.5 nanometers, so that's not terrible, but it definitely could be better. Okay, so that is the scattering spectrum. And again, if you're interested, you could calculate, you can find details of Mie scattering in several books, like Van de Hulst is one of the books, or well, let me just see where, let me look at the sources on this Wikipedia page. So what I used to do mine, Bohren and Huffman, I believe, is what I used to write my own Mie theory calculator, because the equations are kind of explicitly given in that book, but also in Van de Hulst. If you want to go to the original Mie paper, you can, but it's written in German, so if you don't speak German, maybe don't bother with that. Okay, yeah, this part of the tutorial is definitely a lot less looking at Lumerical and more me talking and getting comfortable with recording myself. But yeah, so here we go. We can calculate the scattering spectrum from silver nanospheres. Next up, we want to talk about how to do the absorption spectrum, right? So if your particle has some sort of has a lossiness to it. So if it's a metal, or if you're in a frequency range where there's inner band transitions, we expect that the particle is actually not only going to scatter, but it's also going to absorb some of the incoming light. So we want to calculate that. Okay. So calculating the absorption spectrum. So here I kind of draw this. So what happens is that we have a plane wave coming in and it hits our particle. And this particle is going to absorb some of this light. And that usually turns into heat, or it turns into electrons going to higher level bands. It depends on the physics involved. Okay, so again, we start off with our FDTD, the FDTD setup. We have our total field, scatter field, and the PML. And now we're going to zoom in into the total field. So last time we focused on the scatter field, but now we want to deal with the total field. Okay, so here's our total field. And the way that you would calculate the absorption is by doing kind of what we did with the scatter field and putting 6 monitors forming a box, but now in the total field. And so if we had some sort of lossless particle, or if there was nothing in here at all, we could actually calculate the power in this direction, px1 in this direction, and subtract that from px2. And then we have py1 going up, subtract that from py2, and then pz1 minus pz2. And if we add up those powers, it should be equal to 0, right? Because all the light that enters this medium has to leave it. It's either it's going to get scattered or it'll transmit, but it's got to leave. So if it's basic. If you calculate the powers, power in minus power out, you get 0. So that would tell us now, if we had a non-zero, if this was non-zero, then that would suggest that there is some sort of absorption happening. So calculating the absorption is just as easy as plating this box monitor in here and then doing this calculation, px1 minus px2 plus py1 minus py2 plus pz1 minus pz2. Right? Because this, the power that gets left behind, the power that doesn't end up leaving the box, must be absorbed by our nanoparticle. All right, so now what I'm going to do is I'm actually going to flip px1 and py1 and pz1, which you don't see. So if I flip those arrows, this is equivalent to doing this calculation. So negative px1 plus px2 plus py1 plus py2 plus pz1 plus pz2. Well, this is the same thing as what we did for scattering, if you remember, right? It's just the addition of the powers. Only this time we have a negative in front, and we place our box monitor in the total field region. All right, so let's do that. Let's go into our FDTD software. We're now going to click on Analysis, click on More Choices, go into your optical power, cross-section. Again, it gives us an overly large box. So what we're going to do, we're going to go into here. For some reason, it doesn't actually change the name, so let's call this cross-section, let's call this absorption for now. It's actually usually pretty good form to change the names of all your things. I don't do that because I don't use Lumerical very often. But yeah, so it's already centered at 0 for us, so that's nice. They did that for once. And now we want a box that's in the total field that surrounds the sphere. So I'm going to make this box 140 by 140 by 140 ply. Okay, we click on the magnifying glass again, and here we go. So you can see we have our PMLs, our scattered box monitor, our total field scatter field source, our absorption box monitor. Okay, it's not letting me highlight it, but that's fine. There it is, absorption box monitor, and our sphere. And now we're set up to calculate the oh no, we're not, sorry, we are not quite set up to calculate the absorption because we actually have to do a small correction in the analysis. So we've got to go into the script here. We need to put a negative here, right? Because it's just, you got to do, it's the same calculation as the scattering, but now there's a negative, just from the mathematics. Apply that, and okay. Hopefully it keeps that. So now we can run our simulation. So I actually added in, between the scattering tutorial and the absorption tutorial, I asked it for a few more wavelengths components because I want it to be very smooth. So it's going to take a bit of extra time running here. I think I asked for 201 frequency components to be calculated. But still, Lumerical is a remarkably fast simulation software. I think it would be hard for the average physicist to write a simulation software like this that is this fast, that is this optimized. I think part of the reason, though, is that Lumerical uses floating point precision instead of double precision. So some people would yell at me because I use those terms incorrectly sometimes, but they use the smallest level of floating point precision. Okay, so the simulation ran. I'm done babbling. And now if we click on absorption and we visualize sigma, here is our absorption spectrum. So we get our absorption maximum, kind of close to where we get our absorption, or our scattering maximum. So we actually almost have two peaks here, right? We have one around 350 nanometers and one around 400 nanometers. Now, how does that line up with our calculator here? Yeah, so our oh, here we go. So yeah, we have one around 350 nanometers and one around 400 nanometers. Now, of course, the line shape's a bit different between the two, between the actual calculation and the simulation. And part of the reason for that, part of the reason for this is probably that they're both using different material models. So again, we're using Johnson and Christie, which Lumerical fits to some sort of model, which might not be very good. These guys might be using actual experimental data. And also the FDTD simulation is going to have a lot of error because we're using a rather large step size. But again, we still see the same sort of physics, right? We have this kind of what I call the plateau region in the lower frequencies that we have here. It kind of dips and then plateaus, and here it dips and then it plateaus. So that kind of behavior. We have a slight peak at 350 nanometers. They have a full out peak at 350 nanometers, but that's fine. And then they have a slight peak at 400 nanometers, and we also have a bit of a slight peak at 400 nanometers. And then it goes down into the higher wavelengths. So there you have it. Calculating the absorption for this nanosphere was just as easy as calculating the scattering, and you don't have to do it yourself. So actually, I'm going to change this to scattering just in case I use this file again one day. It's good to know what everything's doing here. Apply. Okay. Now I want to play around a bit here. So if you bear with me, I'm going to change the material of our sphere. So we've dealt with silver, but now let's do a dielectric. With an index of 3.6, so kind of like a silicon sort of thing. Apply that. All right, let's run this. What we expect to see here is we're going to see a rather large scattering spectrum because it's a high index dielectric, and we're going to see zero absorption, or it's probably there's going to be some absorption due to numerical errors, but because it's a dielectric, there's no complex component to the dielectric constant we put in there, so it should have a zero or negligible absorption spectrum. And we'll actually see that. So let's go to our calculator over here. Core type, we're going to say other. And we're going to say, I think I said 3.6. And plot that. And here we go. So yeah, this is what the scattering cross-section looks like. Ooh, that's complicated. And our absorption is essentially 0. It's actually exactly 0. So let's see if it'll get that scattering spectrum though, because that's the cool thing about dielectrics, is that you get all these cool peaks happening. And if your dielectric gets bigger, those peaks go all the way into the visible. So I believe this is what you would call your magnetic dipole resonance. This I think is your electric dipole resonance. This is your electric quadrupole resonance. I'm pretty sure that's what you would name all these peaks. You could actually read up on multipole analysis to find out what all that means. Oh, this is interesting. It's taking a bit longer than it did for the silver sphere, which is surprising to me. Maybe it's because the dielectric has much more complicated resonances. So in the dielectric, the resonances are what we call me resonances, which are kind of similar to Fabry-Perot resonances, where the light kind of gets trapped in the particle. Instead of with silver, it's just, you're reflecting. So maybe the resonance is super strong, and because of that, the fields don't die down as quickly. Well, that's neat. Well, and I guess while we're waiting, I'd like to kind of introduce a YouTube video series for you. Oh man, my internet's really slow right now. Okay, so this is a YouTube channel I never use, so computational electromagnetics. Well, let's see if I can find the YouTube series. Ah, yeah, these guys. So, let's not do that. So if you ever want to go into, if you ever want to write your own code, these lectures by Dr. Raymond Rumpf, he does a bunch of these computational electromagnetics video series, and they're very good. He goes through it and he'll help you out. He'll kind of like go through all the algorithms. He doesn't give you the full code, and he tells you that explicitly. He wants you to write the code for yourself, but he wants to show you how to do, how to write the algorithms. And I think he has an entire series just on FDTD. So if you follow the videos carefully, you should be able to write an FDTD program. Here it is, electromagnetic analysis using the finite difference time domain. And it's 24 lectures. Each of them are about, I'd say, an hour to an hour and a half. And yeah, they're very good. Now, I didn't learn using those lectures. I learned using the book by Taflov. So yeah, that's another good resource. Taflov, Computational Electrodynamics. This is an old version of it, but yeah, if you get your hand on the book by Alan Taflov's Computational Electrodynamics, that's the Bible of FDTD. So if you read that book, you're almost guaranteed to be able to write your own simulation program. And now more recently, there's a book that is kind of, I think it's like Taflov's book, but a more friendly method, and that's the numerical electrodynamics, I believe is what it's called. Let's see. Books. Where is it? Sorry, I guess I'm just killing time here. Numerical. Ah, interesting. Numerical electro. Oh, that's why. Electromagnetics. The FDT method. Let's see. There it is. This one here, by Nunn and Marshall. This is a very, very, very good book. Again, I put this right up there with Taflov, and but it's a bit more user friendly, and I think a few less details than Taflov. If you're at a university, check your university library. I know mine. I can get that book for free through the library. Like I get the PDF for free. So yeah, give that a read if you're interested in ever writing your own FDTD code. It's very fun. Finally, UFDTD. So this I did actually use in writing my own FDTD program. Is this website where this guy puts up his book entirely for free, and it's each chapter is a different aspect of finite difference time domain method, and he does actually give you code. So this is chapter 9, so this is where he goes into 3D FDTD, and you can see that he gives you the algorithms for everything, but he also gives you code snippets for everything as well. Yeah, this one here is a bit more technical. It's a bit harder to get through because you have to like understand what his code's doing and everything, but look at that. Here he does scattering from a sphere. So yeah, it's neat. So those are some resources if you ever want to do your own FDTD calculations. Oh my god, is it still running? Wow, I am surprised it's taking this long. This is fascinating. Okay, well then I'm going to pause and wait for it to finish, and then I'll come back when it's done. So the simulation actually finished about 2 minutes after I cut off, after killing all that time. So, well, I'm glad that it worked out like that. Okay, so let's, first of all, I'm going to visualize the absorption, as I told you. Because we're dealing with a dielectric particle, we expect there to be no absorption. So let's see. Exactly, look at that. It's essentially 0. So it's, of course, as I said, there's going to be some numerical error, and that's what you're seeing here. But because it's 10 to the negative 17, whereas before it was 10 to the negative 14, right? So we're 3 orders of magnitude less, so that's just numerical error. All right, now let's look at the scattering. So we expect it to look something like this. So hopefully that's what we actually see. Let's visualize sigma. And there you go. Look at that. Let's put them next to each other here. All right. There. So we have our primary peak at 375 nanometers, 373, give or take. Right, we have a secondary peak at around 200 and 280 nanometers. For them, it's 285. Sure. Yeah, so you can see that we get really good agreement between the simulation and the actual analytical calculation for the scattering spectrum. So I'm not going to waste any more of your time. This is, I'm going to waste a bit more of your time. Sorry, guys. Going to keep going a bit here. So I want to look at the actual near-field plots for the dielectrics here. So it looks similar. In the long wavelength region, it does look similar. It's got a bit of a dipolar nature to it. And now let's go lower. Okay, you know what? Let's slide it down. And so here's what's neat about dielectric particles is right here you can actually see kind of a magnetic field mode happening. All right, how do I know it's a magnetic field mode? Well, because we have a ring of electric field, right? If you have a ring of electric field, then you're going to have a magnetic dipole mode coming out from the center. So if I go to, oh, did I not calculate H? Oh, I did. I just have to visualize H. All right, let's redraw. So you can almost already see the magnetic field dipolar mode kind of peaking up here, but if I just go in a bit more here, boom, right there. We have almost a perfect magnetic field mode coming out from the center of the particle. And that's because the electric field is actually kind of circulating around the edge of the particle at this frequency. So if you have a circulating electric field, then you have an oscillating magnetic field in the center that comes out of the screen and into the screen. So we get that magnetic dipole mode at around 391 nanometers. So let's see. Yeah, so that's what this peak is right here. This is your magnetic dipole mode. Here's 375 nanometers, so if I were to actually plot that, where'd it go? There it is. All right, visualize H at 375 nanometers. So let's go down to that. There it is. So this is the resonance position for that magnetic field resonance. So yeah, so I have now shown you how to set up a Lumerical scattering simulation. I've shown you some resources and showing where you can learn how FDTD actually works or how to write your own code. But now you have the ability to play around. And this is kind of a lot of what nanophotonics is. It's just simulating scattering from different sized and different shapes of nanoparticles. So this is a very powerful tool. And it also is kind of fun if you go to a conference and you want to show something cool, just show them one of these FDTD movies or videos, as some people will call them. Because, I mean, you show something like this at a conference and people are interested. It draws the eye. And you can actually see this is why the simulation took so long to run. It's because we have this resonance happening inside the particle that just wasn't dying off. And that's a property of dielectrics in the time domain, is that you have this wave bouncing back and forth. Kind of like, as I said, it was like a Fabry-Perot mode, right? It's kind of trapped in this dielectric center when you have vacuum outside. So that's kind of neat. The rest of this video, like all this is just, there's nothing in here. Anyway, thank you so much guys for watching. Again, please be sure to leave a comment if you have any questions or a suggestion. Play around. Just play around with FDTD. Try doing a periodic system, make a metasurface, and see if you can find out how to calculate the reflection and transmission coefficients from a periodic system. Then try to do periodic systems with angled incidence waves with those block boundary conditions. The sky's the limit. So thank you very much.